Welcome back friends to another video of inorganic chemistry, which is based on the inorganic polymers. And my name is Dipanshu Avasthi, and today we are going to discuss about the inorganic polymer, which is silicone. So in the previous video we have discussed about the silicone, their structure and their nomenclature. So in this video we will be going to study about the preparation of silicones, the properties of silicones and the uses of silicones. So without wasting any time, let's start with the preparation of silicones. So the silicones, they can be prepared by the hydrolysis of alkyl or aryl substituted silicone halides, that are chlorosilanes. So for the preparation of silicones, firstly we are going to prepare the chlorosilanes, then we will hydrolyze them and then we will get the silicones. So how we can prepare the chlorosilanes? So firstly, the silicone, they exist in nature in the form of silica. So firstly, this elemental silicone is obtained by the reduction of mineral silica, that is SiO2, with the carbon at high temperature. We expose the silica to carbon at high temperature and we are getting the elemental silicone along with carbon monoxide, which is released as a side product. Then this silicone is converted directly into tetrachlorosilane with the help of chlorine, and it will form silicone tetrachloride. Yeah, we can say tetrachlorosilane is hence prepared. Now after the preparation of tetrachlorosilane, that means the halosilanes are being prepared. Now we will react with the Grignard's reagent to form organosilanes. So hence organosilanes can be obtained by the Grignard reaction. This is the Grignard's reagent, which is RMgX, and we are going to react with any of the halosilanes, means silane halo derivatives of the silanes. In this X group can be any of the halogen, mainly we are discussing about the chlorine. It can be bromine, it can be iodine, or any of the halogen group may be attached here. So these both will react to form organosilane, because our aim was to form organosilane, and it might contain some halogen groups, because these three positions we haven't mentioned anything. It can be halogen, it can be some other group which may be attached to these sites, and hence organosilane molecule is formed and magnesium halide is remain as a side product. It has been precipitated out. So there is generally two types of reactions, two steps of this reaction. Firstly, the formation of Grignard's reagent. After this preparation of Grignard's reagent, we are going to react it with the tetrachlorosilane or any of the alkyl or aryl substituted silanes. So firstly, how we can prepare Grignard's reagent? So Grignard reagent is RMgX, and this X can be any of the halogen group, halide group, we can say chlorine, bromine, iodine. So firstly, Grignard's reagents, for its preparation we will react the haloalkane with magnesium in the presence of ether. Ether is an appropriate solvent to carry out this reaction. It will result in the formation of Grignard's reagent, which is RMgCl here, and this R group can be any alkyl group or the aryl group. Now this resulting etherical solution is treated with cool tetrachlorosilane or the alkyl or aryl substituted silanes. So this reaction is exothermic and it results in the precipitation of magnesium halides. So here we are discussing about the silane, chlorosilane, tetrachlorosilane. So the halides, the precipitates will be of magnesium chloride, and it will form 3 chlorine molecules substituted to the silicon, and one R group is attached to it. So it is the trichloroalkyl silane. When this trichloroalkyl silane will react with the Grignard reagent, then the chlorine molecule, it will get substituted for the R group, and R group will attach to silicon. It will form R2SiCl2, and again precipitates of magnesium chloride will be formed. Similarly, this reaction will proceed, and in the last stage all the chlorine molecule will be displaced by the R group, which is any of the alkyl or the aryl group, and it will lead to the formation of a tetraalkyl silane and with the precipitate of magnesium chloride. So in this way we are going to form organosilane by these steps, but these steps are quite lengthy and it's quite complicated. So due to complication in these steps, due to this process is very complicated, so This has been replaced by a direct process which was given by E.G. Rochow, and it is known as Muellers process. So in this process, methyl chloride or the alkyl chloride, it reacts with elemental silicon at 250 to 550 degrees centigrade temperature in the presence of copper as a catalyst, and it will help in the formation of organosilane containing chlorine as well. But if 4 R groups are present, then no chlorine will be present here. So it's generally the direct formation of the organosilicons, organosilanes we can say, by this process. So in this, silicon is reacting with the alkyl halide at high temperature in the presence of copper, and it is forming the organosilane. And this N group can be any number. It can be 2 methyl groups or 2 alkyl groups, any of the 2, 3, 4, any number can be N. And the number of R group which will be attached to Si, they will attach by replacing this chlorine atom. So if 3 chlorine are replaced, if 3 R groups are attached, then it means only single chlorine molecule is present with it. If N is 2, then R2Si 4 minus 2, that means 2. That R2Si Cl2 will be formed if 2 chlorine are replaced by this R group. So we can see here example, there is methyl chloride, it is reacting with the silicon, which is the elemental silicon, at temperature 250 to 550 in the presence of copper. It is forming dimethyl dichlorosilane, means 2 chlorine molecules जो हैं 2 chlorine molecules and 2 methyl groups, they are attached to it by this CH3Cl. So it is forming dichlorodimethyl-silane. So in the earlier process, we were firstly forming the chlorosilane, and then we are going for the preparation of organosilanes. So in this, we need not to form any of the chlorosilane, we are directly reacting the elemental silicon with the alkyl halide, and no need of Grignard's reagent, nothing, only giving high temperature and copper and forming organosilicons. So the dichlorodimethyl-silanes which are formed here, they are of utmost importance, and other derivatives of the silanes will also be formed, such as RSiCl3 or R3SiCl. So they can be removed by distillation. These subunits, they are of utmost importance because they have 2 chlorine atoms attached to them, and this will help in extending the silicon chain. So that's why this substituent is most preferable, and we are separating this out with the help of distillation. So now we have discussed about the preparation of organosilanes we have formed. Now for the preparation of silicons, we will discuss some other steps. So the compounds of formula R2SiCl2, they are extremely important because they act as a starting material for the preparation of variety of substances. So if we will react it with the basic catalyst at high temperature, then it will favor in the formation of high molecular weight polymers, and they will be linear. If we will react this with the acidic catalyst at high temperature, then it will favor the cyclic low molecular weight polymers. So the desired polymers we can form by reacting them with the given respective catalysts. Now hydrolysis. Hydrolysis is a very important step because this will be helping us to form the polymers of silicons. So hydrolysis, in this we are going to react this compound which was dichlorodialkylsilane, we are going to hydrolyze it with in the presence of water. Hydrolysis is generally the reaction carried out in the presence of water. The water molecule will be break down into H positive and OH negative ions. These react with this alkyl and halogen derivative of silane, and it will be forming R2SiOH twice, which is dialkyl silane diol, along with 2 HCl molecules released out. And its example is, if R group is methyl group, then it can be represented as CH3SiCl2 plus 2 water molecules, and it will be forming the dimethyl silane diol, or we can say simply silanol or silane diol, because 2 H groups are attached and 2 HCl molecules will be released. So now we will discuss about the polymerization, that how it occurs. So the polymerization of dimethyl silanol, it occurs by the elimination of water molecule from the hydroxyl groups which are present at adjacent sites. So these are 2 subunits of the dialkyl silane diol. These are two subunits and these are reacting with each other, and there is a loss of water molecule from them, and they are forming a bridge of oxygen which are joining two subunits. So it is a linear dimer, it's a linear chain is formed and there are two subunits, so we are calling it a dimer, and it can form a polymer if we are taking multiple subunits, and by the this condensation reaction they will be joined to each other and forming the linear polymers. But if what happens if we want to achieve the cyclic polymer or cyclic structures, for that we have to carry out this hydrolysis at carefully controlled conditions. It might be high temperature and high pressure. So when the conditions are controlled and the hydrolysis occurs, then it forms a cyclic structure, and cyclic structure can be tris cyclodimethyl siloxane. Tris because 3 silicon atoms, these are complex structures, so we are calling it tris. Cyclo, it's a cyclic structure. Dimethyl because to each siloxane unit the 2 methyl groups are attached, so it will be combinedly named as tris cyclodimethyl siloxane. And for its preparation, the hydrolysis of the dimethyl silane diol derivative occurs in the presence of carefully controlled conditions. Now we would like to form the cross-linked silicons, because I have discussed in my previous video about the 3 types of silicons which exist in nature. These are linears, cyclic and cross-linked. So cross-linked means there will be straight linking as well as the cross-linking, means branching will be there. So for that it's not sufficient that we have only 2 hydroxyl groups, because it can extend the chain linearly to either left or the right side. It can't extend it to the downward or the upward direction. So for the cross-linking structure we must require trichlorosilane, because it will help the chlorine molecules, they will be displaced or they will be replaced by OH groups. So we will be getting the 3 OH groups, and it can help it to extend its chain across left side, right side and bottom, or if this group is present at the top, then top side, means it will be forming the cross-linked structure only when the 3 chlorine molecules which are attached to the silane, they are replaced by the OH group. So for the formation of trichlorosilane, we will be reacting the alkyl chloride with silane, which is elemental silane, in the presence of 2 HCl at copper at 300 degrees centigrade. It's a Roche process. So we are getting this CH3SiCl3, that is trichloro derivative of silane, and H2 molecule will be released out, and we are going for its hydrolysis, so that this chlorine will be replaced by the OH groups, and it is forming the methyl silane triol, and 3 HCl molecule will be released out. Now we are reacting all these species, all these subunits, and we are getting a cross-linked polymer in which the silicon subunits are attached to each other by the oxygen atoms. Oxygen bridges are formed here. So it's a cross-linked structure of silicons. So trimethylsilanol, which is having the 3 methyl group attached to silicon, having OH group attached to its silanol, so it acts as a block chain subunit, because it blocks the chain length, as it is having only a single hydroxyl group, so it can only extend the chain towards one side, not to the other. So if this group attached to any chain, then it will stop, it will hinder the chain formation. So it acts as a blocking subunit, or we can say it is used to block the chain to get controlled chain polymers. Means if we want to get a controlled length of polymers, we want that it should not keep on extending, but it should stop at some point, then we will add these polymers to control the chain length. So in general, the trimethyl chlorosilane, when they are hydrolyzed, then they form trimethylsilanol, and it is a terminal group, which we have seen here, which act as a blocking subunit. Terminal because in the terminal side it is having one oxygen group, so it can extend towards the single terminal. If we are having dimethyl dichlorosilane, then on its hydrolysis will get oxygen atom, means hydroxyl group attached to 2 sides, and it can extend the chain length across both the sides. So it is acting as a chain forming group. Similarly, if it is hydrolyzed in a controlled condition, then it will be acting as a cyclic chain forming group. It will form a cyclic chain, cyclic ring like structure. So if we are having a single methyl and trichloro derivative of silane, then on its hydrolysis we will be getting at 3 positions of silane, we will be getting hydroxyl groups, which will be helpful for us to form the bridging or the branching structure of the silanol. So here they are acting as a branching or the bridging group, because it is having 3 oxygen atoms, which will be acting as a bridging molecule for the extension of the chain. So now we will move on to the properties of silicones. So after discussing the preparation, now the next topic is the properties of silicones. So they are thermally stable, as in my previous video also I have told. So they are thermally stable. Silicone polymers, they are highly stable towards heat and they exhibit thermal stability up to 200 to 300 degrees centigrade. So they are even stable at this higher temperature. Then the second property is their chemical stability. That means they are stable towards the chemical reagents. When we will react them with the weak acids, alkalis, salt solutions at room temperature, then they will not be affected. These things will have no impact on them. They remain as inert. The strong bases, however, it result into the cleavage of silicon oxygen as well as silicon carbon bonds. So if the strong base, they are exposed to strong base, then only there will be the cleavage of silicon oxygen as well as silicon carbon bonds. So ultimately they are stable, and they are also stable to attack by oxygen. That means they do not undergo oxidation at lower temperatures or at the room temperature, but the oxidation may occur if they are exposed to a high temperature. So it shows that they are generally stable at room temperature, and only if we are exposing them to a higher temperature or some extreme conditions, then only they react with the chemicals, otherwise they are stable. Then discussing about the chemical properties. So chemical properties is that the siloxane bonds in the silicones, they may be cleaved by few of the reagents such as Grignard's reagent or the alkyl lithium or lithium aluminum hydride, which is causing the reduction. So what happens if we are having a polymer siloxane, polysiloxanes? So this polymer, it will break if we are exposing it to the Grignard's reagent. Then this polymer will break on both the sides. This RMGX will attack. At one side R group will attach, and to the other side where oxygen is present, this MgX will attach. So it will break the polymers. Means if we are exposing the polymer of the siloxane to RMGX, then it will break down it. It will form a subunit of it. So this type of subunit will be formed, and on this hydrolysis we will be getting a chain blocking unit that was trialkyl silanol. Similarly, if alkyl lithium, it is exposed to alkyl lithium, then lithium and R group will attach to the one side of the silicon group, and towards this side this lithium will attach. So means it will be blocking the chain. Means this will be forming a subunit which will block the chain extension, which will not allow the extension of chain. So these are properties of these siloxane molecules, and on its hydrolysis it will similarly yield this kind of product which will be having a single side hydroxyl terminal. So it will extend towards the chain towards a single side. It can be left side or the right side and not in any other direction. Means if it will be attached, then it will stop the chain extension. Similarly, if it is reduced to the presence of lithium, in the presence of lithium aluminum hydride, then these both the sides, it will be replaced by hydrogen group. Means it is reduced. The oxygen will be moved out and hydrogen will be attached here. It will form Li2O and aluminum trioxides. Means oxides of lithium and aluminum will be released out. This oxygen will be released out and hydrogen will attach in its place. So siloxanes, they may also undergo the hydrolysis and alcoholysis at higher temperatures, because earlier cases we have studied that they are chemically inert. So at higher temperature only these undergo hydrolysis or the alcoholysis. They are water repellents. They repel water. So why the siloxane molecules repel water? Because they are having the R group. This alkyl group, it act as its, we can say, it protects it from water. It help it to repel the water. So they act as a water repellents. And next property is they do not become too viscous on cooling and therefore are used for low temperature lubrication. So generally what happens with the liquids, when we cool them, then they get viscous. If we are having grease, means if we are greasing something, some surface, so grease in the winters, it get viscous and it is not helpful in that case. But the siloxane, the silicones, they are very advantageous as they do not get too viscous even on cooling. So that's why they can also used for the low temperature lubrications. They act as a good insulators because they are thermally stable. So even at higher temperature also they will be stable. So they can be act as a good insulators. They can be used in the in electrical circuits or in the electrical wires or anywhere, which are more prone to get melted. So because they are highly thermally stable, so they are used as insulators. They are non-stick and they have anti-foaming properties. Then they are resistant to oxidation. Only at higher temperatures they get oxidized. That can be 350 to 400 degrees centigrades. And the silicones, they exist as liquids, oil, greases, elastomers, rubber or resins. So in different forms they exist. These were few properties of the silicone molecules. Now we'll move on to the use of silicone products. So why the silicone products they are useful? Because they are used in the high thermal, high temperature oil baths and high vacuum pump. The silicone molecules are used there, silicone products, at high temperature oil baths and high vacuum pumps. They are used as greases, varnishes, and can be used even at very low temperatures, as I have discussed earlier, because they do not get too viscous even at lower temperatures. So they are used as greases or varnishes because they are water repellent due to the organic groups which are present to them, and they are good insulators. So they are used for the waterproofing and electrical condensers. So waterproofing because water repellent, and they are good insulators, so used in electrical condensers. The next thing is the silicone rubbers. They are very useful because they retain the elasticity at lower temperatures as compared to other rubbers. Because I have discussed earlier that silicone also exists in the form of rubbers, so it's very useful. Why they are useful? Because they retain the elasticity even at lower temperatures than other rubbers. So silicone rubbers are more preferable over the other rubbers, and due to their low toxicity, these are used in the medicinal and cosmetic implants as well. Because they are low toxic, so in implants also we can use the silicone products. So these were few uses of silicone products. We can use the silicone products for variety of purposes. So in this video we have discussed about the preparation of silicones, the properties of silicones, and the use of silicone products. So I hope it would be clear for you. This is all for this video. In next video we'll discuss about the phosphagenes and their preparation. So keep watching, and if you have any doubts then please comment in the comment section, and if you like it then please like and subscribe to my channel. It's all for now. So thank you friends. See you next time. Bye.